Here are the notes for section 10.1. We'll be talking about the counting principle and also about permutations. In real life problems, you want to count the number of ways to perform a task. One way to do this is using a tree diagram. Let's assume that we have a sporting goods store that offers three types of bikes. We have a mountain bike, a racing bike, and a BMX bike. Each of those bikes has three different size tires. The question is, how many bicycle choices does the store offer? So we're going to make a tree diagram. We're going to list this out with a mountain bike, a racing bike, and BMX bike. Each of those bikes has three choices in terms of the size of tire that you can get on it. These are the branches that refer to this as a tree diagram. Make that a 22. You could say that each of these mountain bikes are coming from one store. So we have a store that's offering three mountain bikes, or three types of bikes, and each type of bike has three different tires. So if you sit here and count out the number of ways, there's three bikes for the mountain bikes, three different types. Bikes number 4, 5, and 6 come from the racing bike, and 7, 8, 9 are coming from the BMX. There are 9 choices. That's one way. It's not very efficient, but it does break it down. You can visually see how it is spreading out, why we have so many. Next, we have the fundamental counting principle. Another way to count is using the fundamental counting principle. In this case, we have three choices for the type of bike, and we have three choices for the size of tires. So you could use this as a 3 times 3 to show that we have 9 options possible in our storyline for example number 1. When we have two events, if one event can occur in m ways and another event can occur in n ways, then the number of ways that they both occur would be the product of those two. Very similarly, if you have even 3 or more ways, the fundamental counting principle can be extended to 3 or even more. If 3 events can occur in m, n, and p ways, then the number of ways all of those events can occur is the product of m, n, and p. So for example, if you have a restaurant and you have 5 appetizers, 4 salads, 11 entrees, and 7 desserts, the question here is find the total number of ways that you can order a complete meal. Let's say that you're boxing up meals and you're going to put an appetizer, a salad, an entree, and a dessert into a box. How many boxes would you have with something different in it every time? One item that's changed with a different dessert would be considered a different count or a different box. Well, for our appetizers, and then we have salads, our entrees, and our desserts. Our appetizers, there's 5 of them. Our salads, there's 4 of them, 11 and 7. If we multiply all of those together, we would come up with our number of ways that you could make a meal that would address having at least one of each of those. So we'd come up with 1,540 ways. On page 2, we're going to work with the standard configuration of a Texas license plate, which is going to have one letter followed by 2 digits followed by 3 letters, like the example we have here. What you really need to pay attention to here is the question. And notice how it says, how many different license plates are possible if letters and digits can, that's the key word here, can be repeated. So we're going to have a letter, any letter of the alphabet, then we're going to have a number, followed by a second number, then we're going to have our second letter, a third letter, and then even a fourth letter. 3 letters in a row there at the end. So how many letters do you have to choose from for the first letter of your license plate? Well, there's 26 letters in the alphabet. For any digit, 1 through 9, and also including 0, there are 10 options. You have 10 options for your first number. If you can repeat the first number, then you have 10 options for the second number. If you can repeat the first letter, then you would still have 26, you would still have 26, and still 26 options for the last letter. There's a shorthand way we can write this. 26 to the 4th power times 10 to the 2nd power. That's going to come out to be 45,697,600. And that would be that many license plates. The second question here is saying how many different license plates are possible if the digits and letters cannot be repeated. You can't have the same letter on the license plate a second time. So we're going to do a letter followed by a number, a letter, and letter. For the first letter, there'd be 26 options. For the first number, there's 10 options. For the second number, we don't want to pick what we did the first time, so it has to be something different. So there's only 9 options this time. The second letter has to be different than what we picked on the first letter, so there's only 25 choices, then 24 and 23 choices there at the end. And we would multiply those all together, because we want all of these to occur. So we have 26. Our final answer is 32,292,000 license plates. You have to pay close attention to what they're asking here. Sometimes they'll say you can't repeat the numbers or you can't repeat the letters. So you got to listen to what they're asking. Try to have a good visualization of what's happening. Permutations. Permutation is a key terminology that you need to be familiar with. We're going to talk about another one in the future called combinations, and you're going to have to decipher the difference between the two. So it is important for you to understand what's happening for a permutation so you can identify it in the future. An ordering of n objects is a permutation of the objects. For instance, there are 6 permutations for the letters ABC. I often like to talk about this as triangle ABC, and you would have 6 possible names for triangle ABC. You can name it starting with the letter A and switching BC. You can start with the letter B and switch the AC, or you could start with the letter C and you could switch the BA. There would be only 6 ways that you could rearrange the letters ABC. A permutation, this is called. It's the same 6 letters, but they're in a different order, so we count it differently. We call it something different. So that's why we're counting those. The fundamental counting principle helps you list these out. So how many choices do you have for the first letter? We're working with A, B, and C, so that's 3 options, so we say 3. After you pick one of those letters, how many choices do you have for the second letter? There's only 2 options. Once you have already decided which 2 letters are going to go first and second, how many choices do you have for your last letter? Well, of course, there's only 1. And that multiplies out to be 6 different ways. This is an expression, 3 times 2 times 1. It can be written, a shortcut way of writing that is to say 3 exclamation point. That exclamation point is not really what we call it in mathematics. We call it factorial. So we'd pronounce that 3 factorial, which means 3 times 2 times 1. If it was 5 factorial, then that would be 5 times 4 times 3 times 2 times 1. There's a general format. Anytime you have n to a factorial, you're going to start with that largest number. You're going to multiply it to 1 less than that, multiply it to 2 less than that, multiply it to 3 less than that, and just keep going all the way down to the number 1. So if you had 10 factorial, 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2 times 1. And very similarly, if you have 0 factorial, that's the value of 1. There is only one way to have 0 items. If you don't have any of the items, you arrange 0 items up. There's only one way to do that. Essentially, you didn't do it. That would be the one way. So if you were to evaluate what 4 factorial was, that would be 4 times 3 times 2 times 1. 12 times 2 is 24. We can make a math problem out of it. 6 factorial times 0 factorial. Well, here, that's 6 times 5 times 4 times 3 times 2 times 1 times 1, which is the 0 factorial. That's going to come out to be 720. Here, this looks a little random to you, but later we're going to talk about it. This is 8 factorial divided by the difference between 10 and 6. So this is 8 factorial divided by 4 factorial. You cannot call that 2 factorial. Nothing crosses out. Here it doesn't cross out. So we have 8 times 7, 6, 5, 4, 3, 2, and 1, all divided by 4 times 3 times 2 times 1. Those cross out. We're left with a final answer of 8 times 7 times 6 times 5, which is 1,680 ways, or that would be your value for letter C. Example number 5. If you have 8 runners competing in a track meet, assume there are no ties, in how many ways could the runners finish in a meet? So we have first place, second place, third place, 4th, 5th, 6th, 7th, and 8th place. How many options or how many runners are available to get first place? You have 8 runners available for first place. How many runners are available then for second place? There are 7. And all the way down, 5, 4, 3, 2, and 1. You do want to be careful. You don't want to just start multiplying numbers out. You want to think about the storyline and ask yourself, does the storyline allow this scenario to occur? Is it a situation where you have 8 options and then 7 and then 6 and it counts all the way down? So this would come out to be 40,320. Assuming there are no ties, in how many ways could the runners place first, second, or third? Now we're only looking for those that might get a medal. So how many different ways could the runners be up on the podium for their awards? Well, how many choices do we have for the first place? If 8 runners are going and no one has a specific advantage, then you would have 8 options, and then 7 options for second place, and 6 options for third place. But there is no award for fourth place, so we don't have to go down to 5 times 4 times 3 times 2 times 1. We stop right there. There are 336 ways those 8 people could possibly be standing on the podium if you awarded 3 awards for that race. Okay, this is our final page. For permutations, we're looking at another way to represent permutations, and that's using this NPR, the number of permutations of R objects taken from a group of N distinct options, or objects, is denoted by NPR, and it's given by this formula. So if we're looking at 5p3, we would be using our formula. The N value is 5, the R value is 3. So when we're setting up NPR, our N was 5p3. The larger number will always come first. That's going to be 5 factorial over 5 minus 3 factorial, which essentially is 5 factorial over 2 factorial. 5 times 4 times 3 times 2 times 1 over 2 times 1. Those cross out, and you're left with 60. Very similarly, if we have 4p1, this, if you think about it, you probably don't even need paper and pencil to figure it out. If you have 4 objects and you're going to award only one person the award, how many options do you have? Here you had 5 people and you're going to award 3 people awards. There would be 60 different ways to put them on the podium. Here, if you had 4 people and you awarded just 1, you would think that there would be 4 different ways to do that. We could use the formula if you wish, which gives us 4 times 3 times 2 times 1. 4 minus 1 is 3 factorial. And 3 factorial is 3 times 2 times 1. Those all cross off, and you're left with the number 4. In baseball, a team might have 14 players. How many 9-player batting orders can be formed? Well, if you have 14 people and you're going to arrange, that's the key term here, arrangement, you're going to arrange 9 of them. We're going to have 14 P9. You have 14 possible. You're going to use 9 of them in any order. That means that original 9 could be in a different order. Even one person could be in a different order, and everybody else is the same. 2 people would have to switch to make that happen. Or you could bring in and rotate in new people into that 9 batting order. Anyway, that would be 14 factorial over 14 minus 9 factorial, which is 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1, all divided by 14 minus 9 gives us 5. 5, 4, 3, 2, and 1. You would see that those cross off, and you're left with 14 all the way down to 6. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. You're going to go 9 numbers deep. Just like up here, we had 5 and we went 3 numbers deep. Or we had 4 and we went 1 number deep. So when you multiply this out, you're going to get 726,485,760 batting orders. Okay, last two questions. We're talking about permutations with repetition. This is the number of distinguishable, that's the key term there, distinguishable permutations of n objects where one object is repeated s times. And if there's another number repeated, that would also have an s2, which would be a factorial, and so forth. We look down here at the word Delaware, and we notice that there are 8 letters in Delaware. The A is written twice. The E is written twice. So we're going to say 8 factorial, that's what our formula says, and then we're going to divide it by the letter that gets repeated twice, which would be twice, so we say a 2 factorial. I like to put an A underneath that to represent that I'm talking about the A. And then a 2 factorial again, because there are 2 E's. This you cannot say is 4 factorial. It doesn't work the same way. So this comes out to be 8 times 7, 6, 5, 4, 3, 2, and 1. This is 2 factorial times, or 2 times 1 times 2 times 1. So the 2's are going to pair up maybe with the 4, and that's what you would have left, which is 10,080 permutations. The last example would be Philadelphia. There are 12 letters. The P happens twice. The H happens twice. The I, the L, and the A all happen twice. So you'd say 12 factorial. You'd say 2 factorial because there's 2 P's. You'd say 2 factorial because there are 2 H's. You'd say 2 factorial because there's 2 I's, 2 L's, and 2 A's. If there were 3 of one of the letter, then it would be 3 factorial. If you're using your graphing calculator, you need to be sure that you put parentheses around the denominator. Anyway, this would come out to be 14,968,800.